Hi, I'm John Wang. I'm from LinkedIn. Before I start, next to show hands, how many people who don't have a LinkedIn account? One. I'll get you set up. Okay, so good. So here's my agenda. We're going to talk about LinkedIn, specifically search at LinkedIn. We're going to talk about people search. LinkedIn has the biggest deployment. And then what we did with Lucene, some of the challenges, and we built a bunch of open source projects at LinkedIn, a few of them related to Lucene. And I'll do a demo of one of our new products, but I might do a demo a little earlier on the presentation after I go through LinkedIn. So we're still a startup. We are in Mountain View, founded in 2003. As of October 2010, we are the largest professional social network with 80 million members, over 170 countries, and mostly in the United States, and fastest growing in India. Here's some Alexa numbers, and we're number one in Netherlands. The Dutch like us. So we get about 1 million registrations every 9 days, and that's the growth rate we've been sustaining for a while. So here are the search properties on LinkedIn. People search highlighted, and a bunch of other searches, and we have. I want to highlight a little bit about the recommendation engine called Liar. So it's probably things like jobs you may like, talent match, and more. And we're doing real-time recommendation, so we don't, build a job, ship it off to do that crank for a while, and show you what it is. We want a recruiter to post a resume and right away get people that match the resume. We want to do any type of entity matching from people to people, people to jobs, people to questions. That's the platform we built it on, and that's also on Lucene. And there's it's a different use case of Lucene. We can go into a little bit. Okay, so before getting into that, let me show you a little demo. You guys may have heard this. It's called LinkedIn Signal. We overlay our data while somebody's tweeting already. Of me. So that's showing the real-timeness of this application. So we overlay tweets and LinkedIn updates with LinkedIn social network and the LinkedIn structured data. And to give you a bit better precision of the vast amount of information you get from real-time data. So just go over to this application a little bit more. So in the beginning, you have all these facets on the left-hand side. You can filter by your network, your industry, your company, time, region, school, and hashtags. And you have a search box, of course. And on the right, you have links aggregated from your query. Right? So I can look at things like, right here we do open source search. Let's see what it was. So now, comes back, and because we're in the Lucene conference and my social network are in the Lucene community, and top link is live streaming of Lucene Revolution conference based on open source search. And here are the people talking about it. And here's a little picture telling you I don't know what that is. And the third link is Lucene Revolution. Carrot 2 was actually before yesterday, and it came up today for some reason. And let's do some fun things. From California, we have a big election going on. Let's look at it. Some disclaimer, I'm not responsible for what people say about her. And look at the trending links. That's the kind of data we can get from the social network. And the fastest generated on the fly based on query. And you can see the top company, Meg Whitman for governor, and Jerry Brown 2010. You want to see what people say here? Again, I'm not responsible. So we can also see what Facebook people are talking about Google. That's a query we can save. You can build these custom queries and you can save. Potentially, you can expose as a channels to people that follow you in your social network. You can filter by the network and go on. So I think you see the point. And we aggregate our last 2 weeks of data, about 14 days. I think that's what I want to do for the demo. And let's go back to the presentation. I can go over the background of this a little bit later. Maybe it's in a private beta. Anybody want to play with this thing? I prepared a bunch of invitations for this conference, and I'll send you guys some invitations. All right, let's talk about people search and LinkedIn. We have the richest functionality in terms of different search properties. Oh, by the way, the signal. It's on one shard. We only shard it. And so for the last 14 days, we only aggregate a subset of Twitter users, and it's the one you hadn't found to LinkedIn to have your data fed into Signal. So the index is about 40 million documents, not sharded. And we're able to, from the look of it, a little math, and back of my old calculation, we can handle about 600 queries per second. Okay, so it's real-time update like Signal, but updates on people profile change is not as high as Signal. With facet navigation integration, it's personalized, meaning one of the facets you see on the left-hand side is your social network, and first and second degree. So you can't really add it to the DC index. Right? Updates will kill you. Right? Like if you update one person made a connection, and all his friends are your friends, and you are everybody's friend. So if you're going to do all the update correctly, you kill the system, right? So it's not in Lucene index. We actually do external join on faceting. It's multilingual. A lot of structure and unstructured information. So that's the power of faceted search behind it. We have contextual query segmentation classification. So if you type in, John Java or John Microsoft, it would figure out Microsoft as a company instead of searching for people with last name Microsoft. We have spell check, of course. It's fully distributed, and it's horizontally, hierarchically scalable, and it's elastic. Because the people that join LinkedIn in 9 days, we have to add new shards while the system is running. Right? We can't shut down everything and rebuild, rebalance the data, because a recruiter will get really mad at us and not pay us. It's bad. We don't do index cache warming because of real-time update nature. Right? You can cache all you want. The second your new document comes in, all your caching is valid. So we can't do a downtime for index optimization because we're global. We can't say, hey, it's 1 o'clock in the morning, nobody's using the site, let's do optimization. It's not an option for us. Some details, we're from 5 million members per partition, and we have 2 partitions on the node. Okay, we have 17 partitions right now, 11 applications, 11 brokers, and the peak to trough ratio is about 5, and QPS is 200 per node. I'd like to ask your question, what's your QPS over, right? Because you can always buy machines and applications to multiply your QPS. So per node isn't bad. And I want to add a little bit more. When you save latency on the node, even if you're horizontally scalable, you save a lot, right? Let's say you have 10 replications, right? Times 17 partitions. So every little bit you save on one node, it multiplies. The cost you save multiplies. The bigger you get, the bigger the gain you get when you work on latency. For us, 99% latency is 100 milliseconds. We have a lot of horrible queries, like more than 30 with 10 Boolean clauses. Actually, the Liar project, they actually sent us 1,000 Boolean ors because they want to say, no, IT industry, same thing as software industry, we boost a bunch of ors. And ors normally don't play well with a search engine, so we had to do a bunch of things different. People search requirements, real-time, faceted, distributed, and performance is important. I think I mentioned a number yesterday. Okay, they cut off my slide because they want to tell people that how many inquiries. Okay, so some architecture. So picture 1,000 words. This is basically what it is. When an update happens, it writes to the database. Everything's updated asynchronously. We can update the spell check index, member index, and we pump it into a search cluster. And then you have a business logic here that talks to different services, put things together, and present it. It's pretty standard stuff. So now, if you look at the little box on the right-hand side, on the DB side, so how does data go from DB to the index? That's an interesting question. We have some kind of proprietary software that takes the database, perform a select, and add a trigger on column saying there's updates, and then take the Oracle's commit number as an event, send it to whoever wants to listen to this data channel, and we can then indexer is listening on that data. But the feed into the indexer is generic in such a way that you can listen anything with a version. Why is the version important? Well, in a distributed setup, consistency is hard, right? The distributed system. You get durability out of it easy, right? Because you just have replication, you get good durability. For us, we get isolation and atomicity by having a stream indexing model. So consistency is important because if you have replication and they are out of sync, you need to somehow get back in sync. If one goes down, you need to be able to catch up with the nodes of the same replication. You can put everything in memory, and you go down, it takes you forever to catch up, right? If you have 80 million documents in a Oracle table, you do a select and referral scan, and just wait. And it's pretty much not going to happen in a while. So if you have a version stored with index, knowing it's a checkpoint, know where you started from, you can go from there, from your source, and that's exactly what we do. And you can use that, this version can be anything like timestamp, commit number, whatever, or some kind of incremental number you want to run. The assumption is all updates to the index is idempotent. Right? You can reapply. It's actually a good assumption to make because if you look at all the messaging system that's coming out, the Yahoo's, Hedwig, Bookkeeper, all that kind of stuff, assumes that data has been guaranteed to get you in order at least once. Right? That's a trend where the messaging system are going. To build a stream model, idempotency in the data is improved. So this is our search cluster. So we have this data stream, and these different nodes listen to it. And because each replication, so each node can multiple replication shards, have a checkpoint, and search services talk to the keeper, report to the keeper, who I am, where I'm at, and then that data is notified to the broker or the client. And at any time, the client knows which shards to go to and how many replications are. And you can actually write a routing layer to do round-robin routing, hash, red hash, whatever. So this is our stream indexing model. Eventual consistency is important. So that's why it's very, very hard to do a push model. Like just send an index request. And we need to broadcast to different nodes, and you don't know where you are. One goes down, how do you catch up? right? How the person, I'm this replication, I failed at a certain point, and give me the data again. It's really hard to send that message across. So we chose stream indexing model. And indexing latency. What does that mean? Well, I mean, when a document, the time between when a document is submitted to the system and when it appears in search result. That's indexing latency. And I like to add another requirement based on what we run into. That time shouldn't grow. Right? If I add a document now and it will appear half a second later, as our index grows, then you add another document in there, a minute goes by, then it shows up. And you see that growth, and that's bad. We want to have more of a consistent, flat latency, and that's reasonable. So we built open source, a few open source projects on top of Lucene. Done a lot of customization. We have a real-time indexing system on top of Lucene. It's Apache 2 licensed, and models exactly what we have. And you have a slave process listening to data, some data stream, database, log files, whatever, and you add a piece of custom code called interpreter, which takes your data object map to a Lucene document. So it's like a transformation layer. And then it writes a Lucene. I'm not going to get into details how that works. The Zoe maintainer sitting right there, so he can also answer questions for you afterwards. Why Lucene? So open source is free, good, because we can't afford to pay per core, right? When we work, because we want to add machines. It's Apache project, so we have some branding going on here, and Java-based, and we have a really active community. You guys being here is a testament of that. And Lucene is actually pretty fast. Usually people see, Java, they think slow. Lucene is actually pretty fast. One very important thing that's mentioned a lot is the incremental indexing support. We looked at MG4J, a bunch of other open source search packages. Well, being able to update incrementally is crucial for us. It actually makes real-time indexing possible. It's very customizable. You can have direct access to term listings, derivative table, and everything. And they have a very strong committer team. They're very performance-oriented. And I see a lot of places in the code, they do code tuning down to like move a couple assignments out of loop, avoid a method call, things like that to get performance. It's actually very important when you are, there's a lot of tight loops in the search logic. And saving an assignment will actually help. Lucene and LinkedIn, it's highly leveraged. We just did a huge migration from 2.4 to 2.9. It's pure Lucene. We haven't started an effort for an ally Lucene variant yet. And we have a bunch of open source projects built on top of it. So this is my view of the Lucene library in terms of layer. And the bottom layer is the forward logging mechanism. To write bunch segments out, then you merge. It's actually proven technology like BDB uses it, BDB Java version uses it. Then it reverts the data into inverted index structure, written down as a segment. And you have APIs to access the data. Then on top of that, you have a ranking library with searching, collecting, sorting, whatever. Then you have a data preparation layer, analyzers and stuff like that. So we customize on every different levels in this picture. So we wrote our own sorting framework because the new 2.9 sorting didn't work for us. We want to abstract the logic away from knowing the priority queue that's consuming sorting API, but they actually put it into the sorting API that we can't handle. We enhance the field cache two different ways. We don't do lazy load. We don't want to do on a query time because we want to load at the next loading time. That's hidden from the user search time. And we added more information to field cache. We also expose the term frequencies, frequency, dot frequencies, and minimum and maximum dot equals, given a term. And we wrote a segment merge framework. So this actually was discussed quite a bit on the mailing list. So when we built the real-time indexing system, we saw this GC-like effect, right? Everything's going really cool, everything's running, then all of a sudden, the system halts. You see big spike, and search dies. And then what happened, everything was fine for like 10 hours. So what really happened underneath was that the way Lucene log merge policy works is, you take small segments made into, not so small segments, and kind of works its way up. At some point, you're going to get in a case where two big segments merge. Merging stuff isn't that bad. What happened is everything you have warmed up in the file OS file cache gets thrown out. So all your search happening concurrently are hitting this. And that's what kills you. So we kind of want to spread that cost around, right? So it's okay. I take maybe 10 milliseconds more every 5 minutes. Then 10 hours later, I die. Right? So we wrote a new merge policy. Idea is we know that only consecutive segments can merge. And we want to have the result index between segments to be very balanced. Right? So, so we can calculate variance of size between the dots between every merges. And we can build a graph and apply, and think about the problem as a query segmentation problem. And apply the Viterbi algorithm on top of it and produce the most optimal merge policy. So what you're going to end up is n segments you identify ahead of time of equal length. So which spreads the cost around. So some challenges. So distributed, we need to be distributed, we need to be real time, we need to support fast search, right? Partitioning. Every distributed search system, you need to figure out what do you partition by, right? You partition by time, what it does. You partition by randomly, dog ID, or you can partition by, in our case, a range of member IDs. The reason being we can expand elastically. We need a dynamic cluster management. That's what we built. Off the bookkeeper, meaning if you want to add a new node, new partition onto the system, it should just work. I don't need to shut down load balancers, configure load balancers, bring things up, and we're not a DevOps world, so that turnaround is actually pretty slow. We write software assuming a dedicated search ops person will be able to handle everything for us. That's not. So real-time updates, stream updates, low indexing latency, low maintenance, just mentioned. Faster search, right? So we built our own faster search engine on top of Lucene. We're not a solo shop because mainly the real-time nature that we need. So it's easy to pass it on the data that's in the index, right? They're single value data, they're multi-value data that's in the index. It gets kind of tricky when you have the facet values you don't know until runtime. Example being last join, right? So you don't know what now is until now. So you calculate the bucket, the time range bucket at query time. So you need to be able to do it at runtime. So we call it runtime facets. And also the social graph I mentioned, you don't know about your social graph until a person does a search. Right? So we wrote a framework that you can implement your own code into our system that you can build different types of facets around. And you can compose a new facet handler from different facet handlers. The way we handled the last join problem is we took a runtime facet handler, it doesn't load any data, it just builds these buckets at runtime and then gives down to the static time facet. So, going back to the liar problem, when you have 1,000 work queries, how do we do that? Similar to time, right? Range queries. When your granularity is small, you want to say, last week to now, and you're storing in terms of seconds, then that work query tends to be pretty large. So we leverage the forward index and the invert index together. So we figure out the query time. What's the expected hit count that you're going to get for this subquery, and to choose, do you go to the iterate on the inverted side or you iterate on the forward side? The behavior is, if you have a lot of orders, chances are you're going to hit pretty much everything, right? But you still need to score them and all that kind of stuff. So the gain you get from skipping on the traverse and the inverted way is not that a lot. So you might as well just walk it forward. And so I did some benchmark. When the work query goes to above like 5 or something for iterating forward way generally, and actually plateaus out because it grows with respect to number of documents, not number of clauses. A number of documents is easy because you can shut it. Some things we want to do for the open source projects we build and leverage them into LinkedIn. We do fast scoring first already. So when you search for in the search box eBay, right, and the company can hit, you're going to have one selection of eBay and pretty much nothing else because you search for eBay. Does it make sense? Yeah. So that's a bad fast to show at top, right? Useless. So we want to assign a score to that fast by looking at the distribution of the accounts on the query at runtime. That's what we call facet scoring. We can also do facet value scoring, meaning if you look at the facet counts, its number of hits match this value, right? It's kind of analogous to term frequency. Yeah? Makes sense? So if you look at the current, if you want to sort by accounts, it's basically score on PF only if you want to map it back to the search word. But it's not always good, right? So give you an example. We did some derived data analysis on skills, right? So people with Lucene skill have Java skill as well. Make sense? And everybody has C Java skill. By looking at a resume pool, everybody knows Java, everybody knows C, everybody knows it's not. And so whatever you do, you're going to see those things show up on top. And that's the IDF effect coming out, right? You want to normalize based on that. You want to normalize field based on it. But you want to do more. You want to do recency and all that stuff. So we want to expose a general framework for facet value scoring. So we want to handle push model for index, I said earlier, and still keep eventual consistency. We want to leverage things like these distributed logging systems. So we build a log internally to the distributed system. So you write to the log with an offset and a version. You can keep track from the log. We want to enhance indexing API. I've been playing around with leveraging the annotation support, like in Hibernate Search, that you can just hibernate. You can just annotate your data object and not even have to write the interpreter object that I said earlier. And we want to leverage the new Lucene features. I'm really looking forward to Black indexing real time. The Michael Bush, the mics, and the media. And we want to write more plugins and more facet handlers that's coming out of the box. And performance. So some takeaways. Well, latency is important. Everybody thinks, hey, I can write my system to scale horizontally. I can infinitely scale, right? Because it's horizontal, right? But each node still has to be fast. Yeah? If you still need to watch latency. So if you take 20 milliseconds, average latency, and you do some clever stuff and cut it down to 100 what you really did, you multiply that cost across all the machines. Right? If you have 100 machines in the grid, you've doubled your capacity. And that grows with you. Does that make sense? So it's very important. Search application. Let me just back in. So have you guys heard Steve Saunders talk about web UI? So I accidentally went to one of those. And it's actually pretty interesting. The times, if you look at the entire application, right, you have about, for search application, you have about 900 milliseconds to play with. Because after 900 milliseconds, the instantaneous field goes away, right, of your application. So if you look at the entire application, back-end time for latency is actually very, very small. Right? So there's time on the network. There's time on rendering UI, executing JavaScript out images. There's tons of stuff you can do on the UI. It's really not in the backend. So when you're building the application end-to-end, think about the entire application, not just the backend. I'll give you a little demo about that. It's called pinging. Pinging Google, 56 bytes. It's 140 milliseconds up to 400 milliseconds from here. Right? I'm pinging. Facebook. You see that, right? So you pretty much lost 200 milliseconds right here on 56 bytes, right? And you know how TCP works. If your web page is big, you go back a few times, you add all that up. So writing a good front end is important. I learned to appreciate that a lot overall over time. And understand your asset needs. Right? Do you really need strong consistency? Right? Do you really need when you add the data, and also ordering, right? Do you do global ordering? Is that important to you, or per some kind of logical ordering, partial ordering? Right? For us, it's important for each member to the operation that applies to your profile. Preserving that order is important, right? You can't say, well, I updated this field. You translate to another, delete and update, and I swap. You get pretty mad at me. So your profile goes disappear from index if I loop and mix up their order. It's okay if another person's operation and your operation, that order is different. So it doesn't really matter if another person updated their profile before you, even if your request got in before the other person. That's generally acceptable. So understanding requirements. Assumptions can really bite you. So we made some assumptions, I think, at that point we didn't think was bad. Assumption one, array access is fast. Accessing element array is always fast. Not necessarily true. Under really large arrays, under high concurrency states, it's not that fast. Assuming that segmented updates, the really thing is going to help you in your search application. Not sure if you're doing fast. Social search. We're getting into the era of social search. Facebook, Twitter, LinkedIn are actually doing more of that sort of Google as well. And you have to really appreciate the speed of security, the speed of information flow security. I'll give you two examples. When I was presenting Signal to our board, it's on last Tuesday morning, around 8-ish or something, most of the time. And I was out there playing with the product. Then I saw a tweet. It says, Michael just signed. Right before the AOL TechCrunch deal. Right? I got a tweet because I'm a second-degree person that went from LinkedIn to TechCrunch. And then they wrote a TechCrunch blog article, and those people started tweeting the link. Right? And on the Signal, that article came up. Link number one. There's another link article came out, I think, by another person. People are tweeting about that. And you can just see real time these articles move around until it's watered for a while, until it settles down. That's about 4 hours before any news broke out about what happened. We found out literally 15 seconds after it was signed. You have to appreciate, with a social search, the power and the speed of information. Also security. Your understanding of security is very, very naive about when you're in a social context. So Facebook blog, right? So you guys heard the news about somebody signed Mark Zuckerberg to some kind of group that I don't think he wants to be in. Facebook. When Foursquare checks you in, your friends know about it, and they like it, and that propagates to their friends. Right? Pretty soon, the world finds out where you are, and you can build a website called robthishouse.com by building Facebook APIs. So think about that. Of course, leverage. You want to leverage open source community, open source software, the community, and contribute back. So these are open source projects at LinkedIn. We have a special domain hosting projects. The group I'm in LinkedIn called Search, Network, and Analytics. We built Voldemort, distributed QB store. It's a Java implementation of Dynamo. Bobozoe Sensei is a distributed real-time fast search stack. Kamikaze, again, the author and maintainer sitting right there, is a word index and compression library. We want to actually put it into a Flex index and deploy that into Lucene 2.0. That's coming straight out of West Lab. That's publishing on that most recently. Brati is a super fast KB store. We found so Baltimore is distributed layer for KB stores, right? So each store, right now we're using BDB, and for certain cases we think BDB isn't that fast. So we wrote a store is about, I think, don't quote me, about 5 to 10 times faster than BDB. Because BDB, I think, was written when they didn't think memory was cheap. Norbert is a dynamic cluster management sensei, and associated is on top of the keyword. And that was presented as Scholar 1. If you find them interesting, please send us a resume. I'll give you 2 invites. Let me go back. Before I go to Q&A, let's go back to Signal. So, when we are building this, we discover certain interesting things about this application. When you build a product, right, the original idea was have an idea, you mock it out, right? You write a real prototype, and it works. Right? That's the flow. It's not true with data files. Right? You can do that, and when you get real data, it's like crap. What happened with this is trending links is a great idea. Originally, the trending links is really just a facet, right? It's just aggregate the count of the article. So we kind of collapse article and article ID. We realized people spam. They spam Twitter. Even people on LinkedIn, they spam Twitter. So you see like astrological articles always win because people care about their zodiac, I guess. So we need to do something. So that actually motivated us to do facet value scoring. So we want to be able to collapse on unique counts. So when you vote on an article, you vote once. You don't vote 1,000 times. Just push it. It's like the spamming problem again when we do research, right? Recency is important. Recent articles are important. And we want to also do connection strength. Want to make sure not everybody only gets 1 vote. Maybe some people get maybe 2 votes, some people get half a vote, depending on your social graph. Make sense? So you want to do all these kind of stuff on on facets. And let's take a step further. When you have tweets, you understand, billion searches that we're doing, we have 90 million updates, tweets a day right now. It's a lot, right? But the second you add gestures on articles, it blows that in broad. Right? When you have Facebook, how many Facebook likes do you think people had, like when they launched? don't quote me on the number. I was told by our PM guy. He's normally right. When Facebook launched the Open Graph, when you can put, they syndicated like things around the page, it got 1 billion a day. So be able to handle that kind of load and actually factor into the system, it is a challenge.